Hi guys, so in this video we are now talking about polytropic process. So the term polytropic was originally coined to describe any reversible process on any open or closed system of gas or vapor which involves both heat and work transfer, such that a specified combination of properties were maintained constant throughout process. In such a process, the expression relating the properties of the system throughout the process is called the polytropic path. So a polytropic process is an internally reversible process during which PV raised to n is equals to C. A polytropic process is a thermodynamic process that obeys the relation this equation PV raised to n is equals to C. And for the processes, we have P1 V1 raised to n is equals to P2 V2 raised to n. So where n is any constant. So the n is varying varying according to their processes in such as isentropic process, isothermal process, or isobaric process or isometric process. So we conclude that the n becomes or we have where n becomes kind greater than 0 or equals to 0 but less than less than 1. So this polytropic process, we can describe this in terms of PV diagram. So for illustration for this, we have PV diagram. So assume that your polytropic process describe this in this curve. So this curve is obeys or according to PV raised to n is equals to C from the uh, initial state to the final state or to the state 1 to state 2. So the area under the curve is of this uh, PV diagram is equivalent to the work done flow. So if we creating a strip for this, so the area of the strip is equivalent to length times width, where your length is equivalent to the varying pressure, and your width is the thickness of this uh, area of this boundary. So we could say that your area of the area of um, your strip is equivalent to pressure times the differential volume integration of PdV from limit to 1 to 2. Okay. So for the is diagram, we have this illustration. So assume that your your curve according to PV raised to n is equals to C. So nga ni ang curve. And the area under the curve for this is equivalent to the heat of your process or the heat transfer. So the polytropic process equation can describe a multiple expansion and compression which include heat transfer. So mo ta kung giingon ganiha nga your uh, your polytropic process uh, dependent to any kind of process such as isothermal process, isentropic process, or uh, isobaric process, and isometric process, or any kind of processes according to different kinds of gases. So in relation for the PV and T for the polytropic process, so we have this equation. So P1, B for the relation between P and B, we have P1 B1 raised to N is equals to P2 B2 raised to N for these processes, for this polytropic process. So in relation between T and B, we have this equation. So T2 over T1 is equals to B1 over B2 raised to N minus 1. And for the relation between T and P, we have T2 over T1 is equals to P2 over P1 raised to N minus 1 over N. So this equation derived na nato in previous discussion. So di na nato ni i-derive. So for the derivation of non-flow work, so we have this equation. So ato na ning na describe kani nga equation in previous discussion. So we have this work non-flow is equals to integration from limit 2 to 1 P times differential volume. And we could say that where PV raised to N is equals to C, or your P is equals to C over V raised to N. Ato lang gi-divide into V raised to N. So, if we substitute this pressure to this equation, so your equation for this becomes integration work and flow is equals to 2 to 1 integration for CdV over V raised to N, or your equation we can rewrite to this form. So work done flow is equals to C integration from 2 to 1 V raised negative N dV. So by power rule or the rule for integration, so we have this equation, or this equation becomes C times V negative N plus 1. So for the power rule over D negative N plus 1 times raised to 2 from the limit 2 to 1. So your C, we know that your C is equivalent to PV raised to N. So hence, your work non-flow becomes PV raised to N times V negative N plus 1 over negative N plus 1 from the limit from 2 to 1. Or your work non-flow, if we multiply this equation to this equation above, so your equation becomes V2, or we substitute from upper limit to the lower limit, so your equation becomes V2 raised to negative N plus 1 times P2B2 raised to N minus B1 raised to negative N plus 1 times P1B1 raised to N over 1 minus N. So if we multiply this V2 to this uh, V2 raised to N, so we can cancel uh, this equation, or raised to negative N plus N. Also this equation, so we have negative N raised to N. So we know that any number raised to 0 becomes unity or equal to 1. So your B2 becomes, may bilhin na lang is B2 raised to 1. And then also to this equation becomes B1, or B1 raised to 1. You know. So your work non-flow becomes, or the equation of this work non-flow becomes P2B2 minus P1B1 over 1 minus N. Or by applying the ideal gas equation of state, so we have PB is equals to MRT. So your equation above, so marirewrite siya into form mr T2 minus T1 over 1 minus n, because your P1, P2 B2 is equivalent to mr T2 and your P1 B1 is equivalent to mr T1. So your MR is a common factor. So ato ipagawa, so morning ani ang yung equation. We have MR T2 minus T1 over 1 minus N. Okay. So for the change of internal energy, we have this equation. So change of U is equals to mCB T2 minus C1, where your CB is a specific heat of constant volume. So for the heat transfer, so by applying the first law of thermodynamics, so assume that your kinetic energy and potential energy becomes zero, and your work steady flow becomes zero, and your isa pa, work steady flow and your energy flow becomes zero. So ang may bilin na nga equation becomes Q, or heat, is equals to change of internal energy plus work non-flow. So we know that your change of internal energy is equivalent to mCB T2 minus T1. And your work non-flow, derive na to in the previous dis, discussion. We have this mr T2 minus T1 over 1 minus N. Okay? So as we observe that your T2 minus T1 is a common factor for this equation. So we have this equation. So mCB plus mr over 1 minus N times T2 minus T1. So by dual of this equation, or using or using or by multiplying this equation, so your equation become like this. So m cb minus cbn plus r over 1 minus n. We know that ato ni times becomes mcb times mcbn. So your m becomes a common factor for this equation above this equation. So ato mapagawas. So mo na lang mahibilin cb minus cbn plus r over 1 minus n, then times T2 minus T1. So we know that your CB is equivalent to CP minus R, or your R is equals to CP minus CB. So kana. So pwede siya may ma-rewrite into form your CB becomes CP minus R minus CBN plus R over 1 minus N. Okay? And then we know that your specific heat ratio is equivalent to Cp over Cb, or your Cp is equals to Cb times K. So we can rewrite this form into, or makancel ang R. So we can rewrite your Cp becomes Cbk minus Cbn. So mo na lang may bilin kay ang R na to makancel. So over 1 minus N times T2 minus T1. Okay? So we know that this Cb for this equation is a common factor. So ato pagawas. So ang may bilin na lang is mCb times K minus N over 1 minus N times T2 minus T1, where your Cn is equals to equivalent to Cb K minus N over 1 minus N. So kani nga equation is equivalent to Cn, or pwede nato ang heat transfer nato pwede nato ma-rewrite into form Q is equals to mCn times T2 minus T1. Okay? So for the change of enthalpy, we have this equation. So change of H is equals to MCP T2 minus T1. So mura gyud yung timan na no kung if change of internal energy is inyong gamiton nga specific heat is constant volume. For the change of enthalpy inyong gamiton nga specific heat is for constant pressure. Okay? For the change of entropy, we have this change of H is equals to MCN ln T2 over T1. So, kani nga equation, giderive na nato in the previous chapter. Okay? For the steady flow polytropic, so we have, by applying the first law of thermodynamics, we have Q is equals to change of P plus change of Q plus change of H plus work steady flow. Assume that your potential energy becomes zero and your kinetic energy is equivalent to zero. So, may bili na lang is Q plus change of H plus work steady flow. Also, your work non-flow no, becomes zero. So, ang equation ninyo may ani, work steady flow is equals to Q minus change of H. Okay? So, for the B, we have uh, this equation, negative negative integration from limit 2 to 1 bdp is equals to work steady flow plus change of p, where change of p is equivalent to 0, or your this equation is equals to work steady flow, or or your this equation becomes n p2 b2 minus p1 b1 over 1 minus n, or we can rewrite this equation into form n integration from 2 to 1 times pdv, or this equation is equivalent to work non-flow. So your work steady flow becomes n times work non-flow. So if makuha na nato ang value sa work non-flow, pwede nato i-times into numerical value for n. So let us have an example. So during a polytropic process, 10 pounds of an ideal gas whose R, or gas constant, is equivalent to 40 feet lb over pounds per Radkine, and Cp have 0.25 BTU per pounds Radkine, change state from 20 psia, or pounds per inches squared, and your temperature from initial state we have 40 degrees Fahrenheit to the final state. We have pressure 120 psia, pounds per inches squared, and for the temperature or the final temperature we have 340 degrees Fahrenheit. So the question is, determine the A, and in the B is a change of internal energy and change of enthalpy. For the C is the change of entropy, and the D is for the heat, and E is for the work non-flow, and F is for the work steady flow. In the G, we have this condition: if the process is steady flow, during which change of key, what is the work steady flow? And for what is change of key if work steady flow is becomes zero? So what is the work non-flow process for the H? So first, let us have for A na solution. So by applying the law, ideal gas law, so we have this equation. So T2 over T1 is equals to P2 over P1 raised to n minus 1. So na naman tayo mga value for this temperature 2, or final temperature, in the initial temperature, for the pressure, final pressure, and initial pressure. So for the final temperature we have 340 degrees Fahrenheit. And for your initial temperature, we have 40 degrees Fahrenheit. So, by solving this, we are using natural logarithm. So, para madali ang pag-solve ani. So, input lang ninyo, we have ln becomes 340 plus 460. So, dapat absolute temperature gid siya over the 40 plus 460 over the natural logarithm for this equation. So, ma-divide siya kani mapaubos ang kaninga equation n minus 1 over n. So, for the value nga makuha nato ani is equivalent to n minus 1 over n. So, 120 over 20. So, kana. We have this value. So, ato store, shift store A. Yan. So, we have this value is equivalent to alpha n minus 1 over alpha n. So, shift solve equals, so sakto, 0. So, your n is equivalent to 1.3536 1.356 or 1.36. So for the B, we have change of U. So change of U is equivalent to MCB T2 minus T1. So we have mass na for the given problem in your CB. So wala, di ba? So but makuha na to in terms sa equation nga R is equals to CP minus CB. So ato lang sa nii in terms of BTU ang value sa gas constant. So we have R is equals to CP minus CB. So R divided by 778 for converting to BTU is equals to 0.25 minus CB. So we could have CB 0.1986 BTU pounds per Rankine. And for the change of U, we have 10 pounds times CB 0.986 times 800 for final temperature or absolute temperature. So 340 plus 460 is equivalent to 800. And for 460 plus 40 is equivalent to 500. So your change of U is equals to 595.8 BTU. Okay. And for the change of H, we have MCP. So nanay given value for the constant specific heat constant pressure, we have 0.25 BTU and the mass for these processes. We have 10 times 0.25 times 800 minus 500. So we can get the value of the change of enthalpy, which is 750 BTU. So for the C, we have this equation is equals to MCN ln T2 over T1. So now your CN is equivalent to CV times K minus N over 1 minus N. Okay? So, but wapatay K diri sa kaninga problem. But atong makuha in terms of CP and CB. So, K is, we know that your specific heat constant ratio is equivalent to CP over CB. So we have CP 0.25 and CB 0.1986. So we can get the value of K or specific heat constant ratio. We have 1.26. So we can get the Also, we can get the value of Cn by using this value for key and for n. So we have n 1.356 and key is 1.26. So if we calculate this Cn 0. We have 0.1986 times key, we have 1.26. 1.26 minus n, we have 1.356 over 1 minus n. Your n is 1.356. So we could have this value for Cn 0.0535 bit in terms of this unit BTU per pounds Rankine. So we can get the value of change of entropy. We have this mass 10 pounds, Cn 0.0535 ln over times final temperature over the initial temperature. We have 800 over 500 or equivalent to 0.251 BTU per Rankine. Okay. So for the D, we have Q. We know that your Q is equals to MCN T2 minus T1. So we have 10 pounds for the given as a problem. And for the CN, ato na nakuha value, ganiha, we have temperature, final temperature minus initial temperature. So your Q is equals to 160.5 BTU. Okay? For the E is the work non-flow. So your E is, your work non-flow is equivalent to MRT2 minus T1 over 1 minus N. So we have this 10 and then your R 40 LB feet per LB Rankine. So in terms of BTU, by converting to BTU, we have this 778 nga value over 800 minus 500 times 800 minus 500 over 1 minus n or 1.356 is equals to negative 433.3 BTU. So for the work steady flow, we have this equation n times integration of PdB or your work non-flow. So na naman tayo work non-flow, nakuha na naman nato nga kaning value. So ato na lang i-diretso og times for the n. So we have this 1.356 times negative 433.3 or equivalent to 587.55 BTU. So for the G, sa G kay, wait lang. So natay condition no. If the process is steady flow during which change of key, so what is the work steady flow? So by applying the first law of thermodynamics, so gi-assume nga ang change of key nato sa katunga condition is equivalent to 0. So mao gyapon ang work steady flow nato is equivalent to negative integration of PdB or mao gyapon equals to 587.55 BTU. So for the change of key, so sa katong given condition nga your work steady flow daw it becomes 0. So your change of kinetic energy becomes negative 587.55 gyapon BTU. So we have this value. For the H is work non-flow negative 433.3 BTU. So that's all for now, and this is for this this topic is the last for the this topic is the last topic for the process of ideal gas. So thank you for listening and have a Good day.